Our very first speaker today has come all the way from New York, which used to be, of course, New Amsterdam. So I think we should just go back to that. And it is Michael Goulet, although most of you will probably know Michael better as compiler errors or just errs. Um, Michael has opened over 2,000 PRs to the compiler in the last 4 years, which is impressive, terrifying. Good job. And he's going to talk about almost everything you should know about the compiler front end. And I'm going to fill for about 30 more seconds just for the online streamers because we're still not quite at 9:40. But I'm looking forward to this talk a lot. I know nothing about compiler front ends. This will be great.
Yeah, I guess okay, my voice is on now. Maybe not starting just yet, but this is not a general introduction to the compiler, just warning you. This is mostly meant for people who've already kind of seen a little bit of stuff. So, but my intention is to cache people or to prime people's caches to get people to hear at least about everything once. Then when you have to go back and revisit yourself, because a lot of working on the compiler is revisiting things yourself and learning things yourself, you'll at least have remembered at least vaguely where to look. Right, I guess it's 9:40, so
Perfect.
should we begin?
Let's go. Let's give it up for Michael.
So this talk is a little informal. I'm going to be jumping through the compiler in the source code. I think this should be big enough. I'm going to be using these links down here to kind of jump, so pardon me scrolling around down here. But specifically, who is this talk for? It's for contributors who've poked around the Rust compiler a bit or a lot. People who are interested in kind of a very technical, general overview of how things work in the compiler. By the end of the talk, I don't think you should know everything about the compiler. I might even get through the whole talk. I have 200 bullet points to get through. But at least y'all should know kind of vaguely like how things are structured, where to start to look for things. It's not a teaching guide of the compiler. I'm not teaching you what a compiler is. You should hopefully know like vaguely what a parser and stuff like that are. It's not a gentle introduction to Rust, and it's not exhaustive. So generally, compiler's responsibility is to generate a binary. It also generates libraries. It links existing libraries in using artifacts. You know, we have lots and lots of crates, and kind of one of the philosophies of Rust is to don't write things yourself. Along the way, it's responsible for checking that things are correct and sound. Generally, people like to understand compilers in kind of a phasing order. We start with lexing. We take a raw kind of string of the source code and split it into chunks. Parsing turns that into something more structured. We do lots of lowering passes to turn things into more and more structured representations. Throwing away information that we don't know. Things don't exactly happen in this order in the compiler because we have something called a query system, which I will go into detail about. But honestly, it's pretty useful to think about the compiler in terms of phases. Even if things don't always happen in that order, they generally do, and especially the diagnostics you see will often be in that order. But I'll go into the details about ordering stuff like that when I get the query system sidebar. Anyways, we all start at this entry point called run compiler. It's responsible for doing things like parsing all the options from the command line. Specifically, it parses these options into a structure called the session. The session is kind of a mega uber option holder thing. So it holds like the target option, the host option, all the other miscellaneous -c and -c options. It also is responsible for queuing up all the diagnostics we have in the compiler. So when we emit diagnostics in the compiler, they don't go straight to the standard out or standard error. They get queued up and processed a little bit, and we need to link it back to the source files. We need to make it all pretty and colorful. We might have to emit it like JSON, stuff like that. So the session also stores things like that. It also stores some kind of common we don't really know where to put it type things that need to be shared between parts of the compiler, like code stats. Code stats holds the information about type sizes that we end up monomorphizing in layouts, and we just put it in the session because it's kind of a convenient place to hold it. So code stats has a lock of a vector of these like type info sizes things. But yeah, so once the session is constructed, we can use it for parsing. And parsing happens at the beginning in this passes : parse entry point. I'm not going to go deeply into parsing, so I'm not going to jump into this function. I'm going to jump into a lot of functions in this talk, but it does take the session because of all the things you pass to Rustc, if you've ever invoked Rustc manually, you pass one file and it knows how to compute the module tree based off of all the mod statements in that file. So the only thing it takes is a session, so it knows the input file, and it gives you back a crate. That crate hasn't yet parsed all its submodules because that happens during expansion because like macros can expand into mod statements, and mod statements can expand into macros. So this kind of has to happen in lockstep together. But there's some early parsing options. Like sometimes we just want to print out just the AST of what we've parsed in the main module, or the main/lib module. So we can, if there's -z unpretty, then we will just stop compilation after printing just the parsed representation of the main module. But if we're not, then we go on. So I'm gonna jump into one random function in the parser, parse mod, because I think it's really kind of demonstrative of how the parser works in general. Generally, the parser is a function that it takes in some context. So if you're in the middle of parsing like a struct, it might take in whether like a struct or an enum, and then it returns something called a p-result. A p-result is just a result of a thing, and then a parser error, like a diagnostic error. This is just because most things either parse or they don't. So generally, people just go through, it's a recursive parser, so it's very simple. You kind of just consume tokens and then make choices based off of the tokens you've consumed. So for the purpose of parsing a module, we just loop and parse items. We do some recovery because Rust, as Pietro's talk was yesterday, Rust tries to have good errors. So in this case, we try to consume a bunch of, or any number of missing semicolons, because people might write struct with a semicolon at the end of the struct, because that's what you have to do in C. We want to tell people, no, we don't have semicolons in between items in Rust. And then we push those items into a vector, and return that vector, or it's a thin vec because we try to be optimized in the Rust compiler. And that's how we parse a module. So that's generally the structure of the parser. It's not that interesting. I could go into things like parsing recovery, stuff like that. But of all the things I want to talk to, I probably want to talk the least about parsing, because parsing is one of the things that Rust actually does share with a lot of other compilers. So and the only maybe other thing that I'd like to discuss for people who are writing features specifically in Rust is that we have this thing called gated spans, and it's stored inside the session as well. So whenever you are parsing syntax that is not like ready or is not stabilized, you typically want to associate that with a span, which is it's basically a beginning and end offset in the source file. You want to put it behind a feature gate just so we can make sure to reject that syntax later if people actually try to use it. So in this case, this is parsing impls, like an item called an impl. And if you write const at the beginning of that impl, that's not a feature that you can use yet. Hopefully by the end of the year we have it though. But it's gated behind the const_trait impl feature, and it will later on in a pass called the feature validation pass, we will give you a nice error saying, hey, enable this feature gate if you're on nightly, and hey, if you're on stable, too bad. So that's basically all I have for parsing. But once we have the parsed AST, we will jump into expansion. So expansion and resolution is what we do to turn macros into their expanded forms and resolve most of the identifiers in a crate. So we start out with this crate for resolver, which is this is just a way that we can get that crate that we parsed at the beginning, and we pass it into something called the resolver. The resolver basically just recursively walks through the crate, and when it hits a macro expansion, it expands the tokens and reparses them. It reparses them, and it has some complications around use statements and macros, making sure they have a fixed point. So you can have cases where macros expand into other macros. We want to make sure that those macros they're not unstable, as in like if we try to expand them again, they don't resolve to other macros that they wouldn't have in the first place. Yeah. in this process, we also do something called AST validation. So we walk through the AST. We validate purely syntactical things in AST validation. So, for example, things like unions must have at least one field. Other things like that extern types. I'm not sure if most of you haven't worked in the compiler, maybe never seen an extern type. You can declare an extern type. Extern types can't be generic, for example, because we don't have like template instantiation rules in C++. So once we've done the macro level expansion, we jump into late resolution. Late resolution is something I know a little bit more about, and it looks like my proc macros aren't expanding, so pardon the red lines. But late resolution is responsible for actually resolving all the identifiers and modules and trait items that we have in the compiler. So it's structured. So Rust is naturally scope shaped. So we structure the resolver as a stack of what we call ribs. Ribs are kind of just they're just mappings of identifiers to things. Typically, the thing that the rib is supposed to be mapping is something what we call a res. So a res is basically everything that can, and more POC macro failures. It's either defs, which are items, so like things like functions and structs and stuff like that. Some primitives that have special rules. So like primitives aren't actually declared anywhere. There's no like struct i32 in the standard library. So they have to be built in specifically into the compiler. We have some special rules about things like self-ties and stuff like that that have special resolution rules. Different kinds of self-ties, because self means something different inside of an impl versus in a trait. And locals, which are like variables, and then other things that are more relevant to like attributes like tool mods and stuff like that. So the resolver is, as I said before, kind of in a visitor structure, recursive visitor structure. So we visit things like functions. We try to resolve the things that are like in that function by visiting all the things inside that function. And then we record all the resolutions in something that we then use later for lowering. The one thing I wanted to mention is that lifetimes are resolved kind of differently. They use a whole different rib kind. So they exist in kind of a weird special namespace because they're tick, identifiers, not regular identifiers. And they can be elided. So if you've ever written tick underscore, or if you've ever written something like path, which has a generic and you've just never written the generic on it, we have to synthesize a lifetime in that case. So in order to handle the fact that lifetimes are special, they get resolved specially. And later on, I'll talk about how we actually resolve lifetimes twice because we need to. Right. So let me scroll. As we are expanding and resolving things, we also want to give every item an identifier that we can then use later for lots and lots and lots of different things. And we give these items unique identifiers called def IDs. So as we are going through the expansion, we walk through something called the def collector. The def collector, again, is also a recursive visitor. I will say that lots and lots of things in the compiler are recursive visitors because recursive visitors are great for tree-shaped data. But the def collector is responsible for basically every time it encounters an item, it will call this function called createDef, and it will associate some things we need to know about that like its name and its def kind, which is basically what kind of item it is. And then it will assign it a def ID. It will give us back a local def ID is actually just a def ID where we know that the crate is the local crate, but a def ID is just a local def ID plus a crate ID. And then we use that def ID ubiquitously throughout the compiler. So resolution is done. I wanted to take a sidebar and talk about the query system and more proc macro errors. The query system is basically what we use for almost all computation of stuff after resolution in the compiler. So we have this Omni object called the tie context, and this tie context is given a bunch of methods that are declared through this interesting callback called Rustc queries. And most of every query takes a key, and returns a value, and it's cached, and we can save the information across compilation sessions with incremental. Every one of these queries is backed by a provider. The query providers are just declared in a function. So at the beginning of compilation, we pass in all the providers for queries in a mega table called the providers. And then whenever you invoke a query, if the query system determines that we actually need to recompute the query, for example, if it's the first time that we call a query for a key, or if we haven't cached it or something like that, it'll invoke the query provider. It will take the result from the query provider and hash it and do all this kind of stuff, and then it will store it. And if you call the query again, then it will usually just load the query, the cache query information from memory. Queries can be marked with lots and lots of interesting attributes like separate provide extern. So separate provide extern tells the query provider that it only needs to be implemented for local things, and the way that we get the query result for non-local things, like things from upstream crates, is through another query provider that you can provide. That usually just loads things from tables that we store when we're finalizing the library from the last compilation session. There's things like feedable, which has to do with synthesizing def IDs on the fly, and cache on disk if, which has to do with incremental. So some queries can be very expensive to compute, and we want to know whether or not we need to cache that for the next time we run, so we don't have to recompute it in the next incremental compilation session. Right. So typically we call queries. I got this link wrong. Typically you call queries and you want to get back a value, but sometimes like in the compiler, we want things to be mostly stage-based, as I said before. So we have, and I'm just going to search this one, pardon. We have something called ensure OK, which means we don't really care that what the value of this query is. We just want to make sure it's run. So in the beginning of the compiler, we run ensure OK on a lot of different queries, just kind of give things a general order. And then if the values are needed for compilation later on, we will actually call the query and compute its value. So ensure OK just means I just want to make sure that this query has been run, and not necessarily care about what the value is. More attributes like arena cache make sure that it means that the query provider, for example, closure save names of capture variables, doesn't actually need to return a arena allocated value. It just returns the raw value, and the query will do the caching for you. And then there's some cycle handlers. So the query system doesn't handle cycles. If you have a query that calls another query that calls back into the first query, then it will have an error. But sometimes we want to customize the errors that we have, so we can tell it to actually don't emit an error. We will emit an error for you. So it will instead delay a bug. So delaying a bug means that we will stash an error for later, and we will check that at least one error has been emitted before this. And if not, then the compiler will ice, it will crash catastrophically. So that's the query system. The query system powers basically the whole compiler, and it gives us the ability to, really simplify the structure of how we handle things in the compiler. We don't have to make sure that data is computed by the time we get to some phase in the compiler. We can just call it, and it will kind of be given to us on demand. It also honestly helps us have better diagnostics, because if you need some exotic information from somewhere else in the compiler, we just put it in a query and you can call it, and you can basically access things kind of out of order for the purpose of diagnostics and stuff like that. So we have the AST. It's been resolved. It's been put into the query system as an input, but now we want to lower it into something that's a little bit easier to type check. So we have the here HIR, higher level intermediate representation is what it stands for. And this is the main data structures that we use to type check things in the compiler. So the here is, and I'm getting more proc errors. Let me restart my reload Rust analyzer. Yeah. The here is generally also tree shaped, of course. It is compared to the AST, though, it's immutable. It's desugared, so we lower a lot of things like for loops and dot awaits into kind of simpler representations that we can type check more easily. So we don't have so many special cases in the compiler. It's simplified, so we don't, for example, we don't lower parentheses. We lower tuples because tuples are semantically useful, but parentheses aren't, so we don't lower parentheses. And some state that we have determined from things like expansion and lowering is baked in. So for example, those res structures that are resolution results, they're baked directly into, like, for example, the path expression kind that we have. Typically, things in here are structured like this. So it's basically, we have a struct called item, and inside of it is a kind called item kind. And item kind is where all the interesting stuff happens. That's where we define extern crates and statics and consts and functions and structs and stuff like that. And all of that's shared within kind of the parent item kind structure. And inside of item kind, we just share some plain things that all items have, like spans and owner IDs. So here has its own set of IDs that we only use for here. The main one that you will see everywhere is here ID. Here ID is basically what we use to determine a lot of important pieces of the here using an ID, so we can store kind of data on the side in tables, like type information, stuff like that. Here IDs are identifiers for important pieces of here. Every here ID is associated with a node, and you're able to bidirectionally map between here IDs and nodes. So nodes always contain a here ID inside of it, and nodes can. But then you can load a here ID into a node and then match on what that is. Here IDs are internally composed of an owner ID, as I pointed above, and an item local ID. An item local ID is basically just a U32. An owner ID is important because these are like item level things. So only items have owner IDs. Generally, there's some caveats there that I don't want to get into. But typically, owner IDs are the building block upon which we do a lot of analysis. So a lot of tables take owner IDs in and then store all the information, both for it and all of its children, until we hit the next owner ID. Right. So as I said before, all these IDs are useful for attaching data to type check results. Some queries are keyed off of here IDs. They're useful for navigating the tree in both directions. The tie context, that Uber structure that I told you before, also has functions for kind of getting the parent node of something if you have its here ID, and this is used for diagnostics, for kind of walking up the tree. So if you forgot to declare a variable, then we can walk up the tree to the next block and tell you where to put the variable. Yeah. So how do we get to this here, though? I did a lot of explanation, but I haven't really gotten into the detail of, because right now all we have is an AST. So this happens in here lowering, and so all we do is first we take the resolver results and the crate that we process during resolving. We pass it into something called the item lowerer. This is, again, also a recursively defined thing. So it takes the AST version of something and turns it into the here version of something, and it allocates all of the things in here on an arena. And AST to here lowering is pretty straightforward. It's mostly just validation and kind of shuttling data between one data representation to another. I can kind of walk into it, but it's, again, pretty tree structured. We walk into lowering functions. We match on all the things, and we match on, like, here's lower mod, for example. It takes a mod item in, and it lowers a module by lowering all of its mod children recursively. There's one quirk that I maybe wanted to point out too, is that as I said before, we do processing to make type checking easier between AST to here. So for example, coroutines, which power async blocks, do a bunch of desugaring with its, like, arguments. So because coroutines are like functions that return async blocks, and async blocks are actually just closures in disguise. We need to take all the arguments and pass them into the closure and make sure they're all captured and stuff like that. So this is kind of the most complicated thing you'll see inside of AST lowering. And I'm not asking for y'all to actually read this, but it's basically just like a lot of processing. A lot of the comments in the lowering context describe theoretical pieces of code and explain how they might be lowered in the here, and then go into actually doing that. Right. So at this point, we have lowered the here. And now we need to do, as I said before, that lifetime analysis part 2. And this happens in something called resolve bound vars. Let's reload Rust Analyzer again because I'm getting more procmaker errors. So resolve bound vars, which I'll call RBV because it's a handful or a mouthful, happens where we walk through the here once again, and we try to resolve all those tick underscores and anonymous lifetimes that we lowered during resolution and expansion. We also at this point re-resolve type and const parameters. This is because we have some features in flight like non-lifetime binders that need to know whether some things are kind of higher ranked or not. And resolve bound lifetimes is the first, or resolve bound vars is the first time that we actually have the sufficient information to know whether things are higher ranked or not. So RBV is responsible for doing that. It works on the here and gives us the sufficient information to actually lower into the next representation, which we will call middle. So middle is a pretty kind of vaguely named crate in the compiler. It's the leftovers of everything that wasn't either pulled out into a higher compiler in the crate graph, or a higher crate in the crate graph, or a lower crate in the crate graph. It's just whatever's left in the middle. Typically, though, in my understanding is my intuition is that middle contains all the type system stuff. It obviously contains a lot more, but generally the most important stuff you'll be importing from middle is specifically from a module called middle tie. Middle tie is the Uber module that contains all the stuff for the type system. So like, why do we need another representation? Like, we already had 2 at this point. Like, do we really need another? Specifically, middle tie is very useful for us on the types team because it's the representation that has no fluff, no nothing. It has no spans. It's all the syntax has been stripped away. Even a lot of the notions that might be different for users have been kind of abstracted away. Like, we treat structs, enums, and unions all as the same thing. We call ADTs, abstract data types, or something like that. For example, like if we lower 2 U32 types in vastly different parts of the program, they turn into the same tie in the middle representation. It's the cross-crate interface that we use for API level information about crates. For example, here we basically just throw away when the compilation session is done. But if we want to access things from upstream crates, we'll typically access it in its tie representation, at least at the signature level. We also have mirror and stuff like that. Almost everything in Rustc middle is encodable for this cross-crate reason. Encodable, decodable, so we can store it in libraries. And the lowering process from here to tie is called here tie lowering. So, but I just typically call it here to middle. So it's not ambiguous because if I say here tie lowering, is it going to here or is it coming from here? This is the logic for lowering from here to middle is contained inside this trait called here tie lower. You might ask, like, why is this inside of a trait when the rest of them were just kind of inside of structs? It's because we actually have 2 of them. We have different contexts that we lower things into the middle layer, and it has to do basically of whether or not we're inside of a body. So inside of the braces of a function, or after the equals of a const or a struct, we call this in the type system, we call this a body. Inside of bodies, we can do things like type inference that you can't do at the signature level, or for example, in like a struct field, or like in an extern block or something like that. So to distinguish the capabilities and the responsibilities of these 2 types of lowering, but also to kind of share all the things that are in the middle, like there's nothing different between lowering a U32 inside or outside of a body. We've abstracted into a here tie lower. There are 2 implementations of the here tie lower, one inside of something we call the function context, and one inside of something we'll call the item context. The item context is responsible for item level lowering things. There's a very useful doc comment written by F. Mies, I think, that describes the distinction between the item context and the function context. But the item context is typically what we use to lower things, as I said before, like struct fields and things in the function signatures and stuff like that. It itself also is a recursive lower. Basically, just takes something in its here representation, it returns something back in its tie representation. I didn't have a lot of links to this, but there's functions like lower tie and lower const and lower lifetime, which we also call region. So if I say region at all in this talk, what I mean is lifetime, because region is the technical word that we use in the compiler. But if we are not at the signature level, if we're actually within a function, because obviously functions make things go in the world, we need to do something called inference. So you are allowed to write the underscore placeholder when you mean figure it out for me. I don't know what this is. Compiler, figure it out, and typically it will. And if it won't, then it'll tell you. But in order to do this process of inference, we need something to store all the inference state, because inference can go backwards, it can go forwards. It can happen basically only once we know sufficient information in the type system and stuff like that. So the structure that we use to store things for inference is very helpfully called the infer context. The infer context is basically just a bunch of tables. So inference, specifically, inference is the process of, as I said before, checking things. Inference context is basically just a bunch of tables for type variables and other inference variables. We have other inference variables like const variables and lifetime variables. But the one that you might interact with the most is type variables. The inference context also stores all the lifetime requirements that we need to check at the end of running checking a body, because if you've ever talked to anyone in the type system, we may have told you that lifetime doesn't affect type inference, or free lifetimes don't affect type inference. So what we do is we basically just take all the lifetime information that we've learned about equating types together and store them in the table at the end. It also stores all the hidden types of opaque infiltrate types that were inferred. Inference contexts are constructed using this build function. So tcx.inferContext gives you a builder pattern for inference, and you call .build, and you pass something called a typing mode, which I don't think I'll have enough time to get into, but it basically just says what kinds of things are you allowed to do at this point. Are you allowed to infer infiltrates? Are you allowed to it has some special behavior on specialization, but this will give you an inference context. And once you have an inference context, you technically are allowed to do things like equate type variables and stuff like that. Like if I have a vec of underscore and I call .push one I32 onto it, we should be able to infer that the inference lifetime of that vector is now an I32 by constraining it by the push function. Right. Inference contexts are useful. We have a whole structure dedicated to it because it's because both it needs to store things, but also it's kind of a nice data structure to work with. It allows us to do things like probes, which is a lot of times in the compiler or in type checking, we need to explore possibilities. So entering into a probe allows us to kind of like do things that might have side effects and then roll back at the end, because we only care about, for example, whether or not something works or not. So for example, like in method selection, we want to check all the methods that work. And then if there's only one, then we want to give you an ambiguity error, or we have some precedence rules. We want to check out which impl actually might satisfy a trait, because there might be two that apply, but upon further inspection, only one actually applies. We use probing all over the place in diagnostics. However, one thing that inference contexts don't store is they don't store the trait solver state. So like, what is trait solver state? So like where clauses, we call those predicates in the compiler. And when you call, for example, a function, you need to satisfy the where clauses of the function for the function to be like sound and valid to call. The process of satisfying those where clauses is what we call like satisfying the obligations. So we store predicates and the obligation to prove that predicate in a structure called an obligation. More park microerrors. So an obligation contains some T. It's generic over T because we actually use this obligation for more things. A parameter, which is basically the environment in which you're proving things. So like if you're in a function and you have a where clause that says like, for example, a mutable pointer of i32, like ampersand mute i32 is copy, then you can prove the fact that ampersand mute i32 is copy even if it's not true globally. So having the parameter allows us to prove things that we might only be able to know inside of the where clause. And it also, more importantly, allows us to assume things about generic type variables that we don't know anything else about. For example, if we need to prove that some T implements iterator, then we need to have a param a where clause environment that lets us assume that T implements iterator. It also stores things like recursion depth, so we know when to overflow things in the compiler. But these obligations need to be put into something so they can be processed. And we don't want to make it so that if we prove an obligation and we don't know for certain if it's true, that we're going to fail. So we basically need to hold these obligations in a queue of sorts to process them over and over and over until they finally succeed. For example, if I have a vec of underscore and I want to prove that it's display, vec of underscore, well, debug. If I want to prove that it's debug, vec of underscore is not debug only if that inference variable underscore is debug. So we might not know yet whether or not it implements debug, but we need to wait until sufficient type inference has proceeded until we can prove that it's debug. So we store these obligations that are in flight in something that we call a obligation context. Let's see. The obligation context, which is basically just a inference context, as I said before, plus something that we call a din trait engine. I'm not going to go into the details about din trait engine because din trait engine is only din because we have 2 trait solver implementations today. Hopefully, we will be able to fold that down into basically one implementation of the trait solver, and it will just be what we call a fulfillment context. But that ref silif box of din trait engine is basically just a vector of in-flight obligations that we are in the process of proving. So the obligation context gives us a great API to do a bunch of things like register obligations. So it takes an obligation in, and you can do it for multiple obligations. There's some kind of convenience functions for registering things. Normalization, which is taking a type and kind of simplifying the types, associate types inside of it. So for example, if I have an array type and I say array as into iterator : item, then that normalizes to the item of the array. So obligations are the main object that we use to prove things. One thing I forgot to go about obligations is that they also contain diagnostic information. We have this giganto struct called obligation cause code that contains all the different reasons why we might want to prove something to help us have enough context to prove things and also give good error messages. As I said before, they act as pending queues of obligations that have yet to be processed. If we process obligations, let me see if I find the select. So select where possible basically tries to compute all the obligations that are in process, and if we for certain know that one obligation fails, we will return it in this vector of E. Obligations are also abstract over the kind of error message we want to return because we might not actually want to compute all the deep error messages for why something failed, because even computing error messages is expensive. And then any leftover obligations at the end of processing, we will also turn into ambiguity errors. So basically, if I declare a variable and I never assign anything to it and I never give it a type, then I need to say this variable has no type information. Therefore, we can't prove that that variable is sized, because you prove every variable is sized. That will happen at the end at select all or error, which is basically just select where possible, and then everything else that's left over turns into ambiguity error. Right, so the obligation context is one of the things that you can put obligations into and process them, kind of like the distinction between inside of and outside of a body, between item context and function context. Obligation contexts are usually used for proving things outside of a body. Inside of a body, we have something else called the function context, which is kind of the major structure that we use to do type checking inside of a body for functions. So though almost everywhere else, if you want to just create a context to check a predicate, if you want to If you want to do it for diagnostics, if you're trying to add extra validation for example, adding a new feature to struct or something like that, you'll probably almost always want to create an obligation context. Right. Obligation contexts and function contexts don't support probing. So if you need to prove something inside of a probe, like if I said if you want to test something out, proving predicates might have inference side effects. So if you want to not let those inference side effects bleed into your program, for example, if you're just trying to validate something for diagnostics, you need to create an obligation context inside of the probe. And if you don't, then I think the compiler will ice. So that is all the context that you need. So we can jump into type checking. So again, I hope that everyone here has written a function in Rust, because functions is where all the magic happens. It contains expressions, and all the expressions have types that fly everywhere. And unlike programming languages like C and Java, you don't have to write all the types everywhere. The fact that you don't have to write the types is, I think, one of the greatest things that Rust gives you, but also that you have the type information like Python. So how does all that work? It happens inside of something, as I said before, called the function context. In this, I'm just going to disable Rust Analyzer. Can I kill Rust Analyzer? So, like almost every other thing I said here, function checking is also recursive. We basically want to take an expression, check the expression, and return what type that expression evaluates to. So this is the entry point into checking functions. So it takes a function context that we constructed. Constructing that function context is not that interesting. We basically just take the root of type checking. So every function is its function root, but inside of a function, you can have other things that are type checked with it, like closures and const blocks and stuff like that. Inference variables can flow between closures and const blocks and stuff like that. So we have to check them all together. So a function context just contains an inference context. And it's also recursive. So checkfn, it does some things around handling opaque types, infiltrates. It initializes the locals of of parameters, but the most interesting part of checkfn is where is it? Check return a body tail, which is the entry point into just basically checking, does the body of the function evaluate to its return expression? And the way we can do that is by checking the return expression, and we give it the hint of the return type, and we enter into check expr with hint. Check expr with hint is probably not the function that you'll call if you're implementing new type checking. There's lots of different flavors of this fn check expr star, but they all basically have the same shape. They take an expression or a pattern or something like that in, and they return a tie out. So checkx for hint calls into checkx for expectation. Expectations are basically just saying, what do I know about the type that we're checking from the outside? Where are we passing in to kind of influence things like unsizing and coercions and stuff like that. We also pass in, for example, the args of a call expression, but we eventually bottom out in a function called check expr kind. I think I don't no, I do not have it in here. Check expr kind, and that's the match on all the different expr kinds and check it based off of the behavior that we expect the expression to have. So, for example, literals will evaluate to the literal type. They'll actually usually evaluate into an integer or float inference variable. Binary expressions need to do operator lookup. Assignments need to make sure that the left-hand side is coercible, the right-hand side is coercible, and the left-hand side, et cetera, et cetera. We recursively walk through the here body. We check things as we're going along. For example, as we're going along, we record information. Like, for example, check expr field. When we check that some base type has a field, we're allowed to do auto deref. So we need to store how many times we've auto deref the base. So what we will do is we'll enter into a loop. We'll instantiate an auto deref, which basically is just an iterator that takes the base type in and repeatedly tries to apply the deref trait to it. And we check if each one of these base ties is an ADT, is it a struct or a union, or an enum. We check that it has the given field that we were looking for. If we find it, we write what the index of that field is, because very commonly in the compiler, we don't want to work with names. We want to work with indices because indices are easier to deal with, and names can have things like hygiene that we don't want to have to deal with. We write the adjustment steps, which is basically the number of auto drifts we need to do. We check things like visibility. We want to make sure that all the where clauses that we get from the auto deref apply. We want to check the stability of the field, and then we want to construct the field type by taking the type of the ADT, taking all its generic parameters and plugging those into the field type. Right, and then we want to bubble up. So we return the field type because we want to bubble up this type information for whatever expression this is contained within. As I said, yeah, auto deref is very commonly used in the compiler or in type checking for things like everything that has to do with a dot. We also very commonly do things like coercion. So when we're checking an array, for example, all the array elements don't need to be equal to each other. They just need to be coercible into something similar or something related by coercion. So coercion is not the same as type equality because you can do things like unsizing, and these all actually turn into real statements and real machine code in the compiler, or sorry, in the final binary, versus type equality doesn't actually turn into any real instructions. It's just kind of a type theoretical notion of equality. So, for example, here we check that if the args isn't empty, if it's not just an empty array, we construct this thing called coerce many, and for each expression, we check the expression using the hint of the type information we have in the coerce many, and we coerce that type into kind of basically take the type information out, check the expression, put it back in. And then once we're done, we complete the coercion and we return the element type back up. Right. I'm going to jump over. I was going to go into closure analysis, but we definitely do not have enough time for that. But at the end of type checking, we do this thing called Writeback. Specifically, Writeback helps us prepare all the type information that we have for use in later phases of the compiler. Specifically, we don't allow us to have any inference variables at the end of type checking. All variables should have been constrained. All inference variables should have been turned into something else. So this is the function in which we actually do this processing if we're solving all the type variables in a body. We create this thing called a writeback context and visit all the data that we store in this writeback context. We store all the types of all the expressions in the tree. We store all the information about all the method resolutions and all the fields and all the pattern types and stuff like that. So yeah, we visit the body, check all the closure sizes, we visit closures, we check opaque types, all the casts, user provided ties, things like that. And then we finally return these type check results up after Arena allocating them so they're copy. One interesting thing I might want to point out is that we also do a lot of hacks in the writeback to kind of handle lowering to mir, which is the next stage of lowering. For example, 1+2, the built-in 1+2 operator gets treated specially in mir. We don't want to have to do a method call for things that we know are built-in mir operators. So here we detect that if we have a expression that is a unary or binary operator and the node types are scalar, which is basically they're integers, then we remove the fact that we basically remove that they're method calls at all, and they fall back to being built-in mir operators. All right, so that's type checking. Between type checking in the here level and lowering to the mir level to do borrow checking, we have one middle phase in the middle that we call type tier or thier. I don't know if everyone calls it thier, but I do. You could also call it tier or whatever. But type tier is basically just an intermediate representation between here and mir, which we use to kind of elaborate even more of the information that we've inferred during type checking. We lower things into a table. Into a table-based representation rather than being a kind of a substituted, or not a substitute, an arena allocated kind of tree shape structure. Let me see if I can find X per kind. Jump into it. Also, pardon again for the red. But we lower all the expressions into a very simple representation, like a box just contains an X per ID. X per IDs are just a mapping from ID to expr kinds, or they're actually Thier exprs, which contains expr kinds. We store extra information that we didn't have before, like scoping information, which is very important for mirror lowering. We simplify things like method calls into just basically every single call is just the same kind of call. And we want to store some extra information, like does it come from a here call operator, does it come from something else, because we can lower different kinds of calls based off of things like derefs and stuff like that. Right. So we, again, it's the same kind of structure. We walk through, we visit here, we emit there. The lowering is pretty straightforward. Basically, we just pass in for example, a here expr into something that's typically called mirror something, and that mirror something will return the Thier version of that something. We do some more analysis, or we do some slightly more analysis. Actually, no, we don't do that here. And we allocate it into something that we call a steal, which I kind of won't get into. Two things that we do on Thier conveniently is we check patterns using the Thier, because having all that type information kind of baked into the Thier is very, very useful for checking pattern exhaustivity. Otherwise, we'd have to be looking up types from patterns, and we'd have problems around things like implicit pattern derefs and inference and stuff like that. We also check unsafety on Thier. Can't exactly remember what the motivation for checking unsafety on Thier versus mirror is, but it's probably a good reason. And we do those both before lowering directly to mirror. So mirror is the last IR that I will talk about. It is the simplest representation that we get before we do cogen. It's very flat. Typically, statements in mirror are not tree shaped. They can't have like complex expressions inside of them. They're typically just like local equals, like a local variable equals, and then some very simple expression. And if you want to, we lower like maybe a very complex expression to like 10 or 15 different mirror statements. So mirror lowering, I didn't have a bullet point for that. Mirror lowering is, give me a second. Mirror is conducive to control flow graph type analysis. Expressions and statements in here are flattened to very simple operations in mirror. It's easy to do, as I said before, flow-based analysis and transformations, things like drop elaboration and coroutine lowering and borrow check on mirror. So, and the first thing, and I think the only thing I'll be able to get to in the mirror level is that we also do borrow checking on mirror. And this is because borrow checking has this kind of graph-based, flow-based analysis that is a lot more conducive to do on mirror than on here, because here is naturally like scoped and naturally lexical. So that's why we have non-lexical lifetime and a non-lexical representation of the program. So borrow check is pretty straightforward. Let's restart the server one more time to get rid of the red. It takes the mirror that we lowered, and because the mirror is a completely different representation than the here, we have basically no connection between the mirror and the here. So all the lifetime information that we computed during here, we basically just throw it away. We need to recompute all the lifetime information that comes from where clauses on calling functions. Like if I have some function that you call and it requires that t is static, then we need to compute that requirement somewhere. So we do this by running type check over again. We first take the mirror body. We take all the lifetimes that show up in that mirror body, which are represented using something called the erased region, which means we don't know anything about the region information. For example, CodeGen doesn't care about anything about regions. So we take that body that has a bunch of erased regions in it. We give every single lifetime a unique identifier. Then we do type checking on that. This type checking is interesting because all it's doing is type checking the program to get its like region constraints for. It doesn't expect any type checker errors to happen. No failures are expected to happen. If we find some type of like type mismatch in the mirror, that's either because of a lowering problem or something that wasn't being checked correctly in here. So we walk through this body, we retype check it one more time to get all of the all the region constraints. We visit the here or the mirror one more time to check basically where things get initialized and where things get deinitialized. And in between those points, whenever it is initialized, it's called live, and therefore it needs to have a valid region. Then when we have all this information, we throw it into a graph. We process it using all these graph algorithms that I don't really want to get into, and we check all the constraints are valid. We basically say that we know that, for example, some lifetimes can't that only outlives these other lifetimes. We will emit errors based off of that. So we enforce the liveness constraints by computing all the things we know about this graph, and then walking through it and processing all the informations. We try to take these region errors that are typically pretty abstract and turn them into good errors. I think the name was like 3-part error is what the philosophy of NLL is you want to say where it's initialized, where it's being used, and then where it's being used again where it's not valid. What did I mean here? Yeah, so once we do our solving, then we process through all the regions and we emit errors. And I think that's the last analysis that we do before we get into like linting and cogent, which I don't think I'll have enough time for. Another thing that we need to do during borrow checking is that's actually where we infer all of our infiltrate opaque types, because we need to know what the value of the infiltrate opaque type is, like considering all the lifetimes inside of it. And as I said before, we throw away all the region information from here type checking. So we actually have to do it once again in borrow check. So I think people like to joke, for example, that we could just like not run borrow check and the program will run perfectly fine. It's like actually it won't, because we still need to compute the hidden types, is what we call them, of here. We do compute it kind of in the here as well, but for the whole process to be sound, we have to recompute it in here type check, or sorry, in mirror type check and in mirror again. Right. I wanted to have one more sidebar about foreign modules, upstream libraries and stuff like that. So as I said before, you can mark some queries with separate provide extern, and like this one, type alias is lazy. So we have a feature called lazy type aliases, and we don't want to have to recompute if that type alias applies to that feature. When we're in a downstream crate, so we save whether or not this type alias is lazy. We record it in this final step when we're encoding libraries, where we just record a bunch of things into tables. And that's, I think, it. So yeah, I know there's a lot. I didn't go into nearly as much detail as I needed to. I'm happy to answer questions, I think, after the session, because I don't think there's going to be enough time to discuss things in a session. I used to have this thing where I used to go through things in much, much more detail than this. I kind of stopped doing that. I might start doing that again. Online on YouTube, I think there's one deep dive about methods that I went into a lot of detail. I think people told me that it was useful. But yeah, thanks for listening to me yap about the compiler for the last 60 minutes or something like that. I think that's it.